So this week we are going to continue on with gravity. This week will be important because we're going to clean up some stuff when it comes to two-dimensional vectors. I know in kinematics and forces we talked a little bit about two dimensions. It's really going to be important this week that we understand how to add vectors in two dimensions. First off, just want to talk about this apparatus. This is where we got that big G from. If you remember, big G is 6.67 times 10 to the negative 11. That came from this Cavendish experiment, which took two masses, a larger one and a smaller one, and then it measured the twist that resulted from them being brought close to each other. Now there's a mirror on a fiber, so that twist is actually measurable on a screen, and they were able to identify what G is as well. This comes back in Physics 30 when we start talking about electromagnetism and how we can conduct experiments studying magnetism. Now, gravity, like most everything else in physics, is not limited to 1D. So if we apply the idea that F net is the sum of all the forces, we calculate the net gravitational force by adding those forces together. So if I wanted to know the force of gravity acting on spherical cow number 2, we need to think of, okay, what forces are acting on it? If we think about cow number 1 and cow number 2, there's an attraction between them. You see this red line, this FG, and this FG. They're equal and opposite. That's Newton's third law. If you think about cow number 2 and cow number 3, there's also an equal and opposite force of gravity between those. The net force, though, if we think about where cow number 2 is going to go, if there's a force acting to the left and a force acting down, cow number 2 is actually going to go in this direction. That's the net force. Now, we don't just add these numbers together, whatever we calculate for FG, we need to add vectors. And remember, when we add vectors, we always add vectors tip to. So let's look at the force of gravity acting on cow number 2. So there are 3 identical cows, because why not? This cow is utterly confused, but let's calculate. So FG is big G, M1, M2 over R squared. Big G is big G, 6.67 times 10 to the negative 11. Second to E, negative 11. My masses are 753 kilograms each. So that's 753 kilograms squared. So times 753 times 753. Divided by the distance between them squared, so that's 10 meters squared. And I get 3.78 times 10 to the negative 7. Now, if we think about cow number 2 and cow number 3, there will also be a force of gravity between those. Now, because the cows are the same size and the distance is the same size, this will also be 3.78 times 10 to the negative 7 newtons. Now, it's relatively small because cows are relatively small compared to planets and stuff like that. Now, we need to think about, okay, what direction is the net force going to be on cow number 2? This first one we calculated is to the left. The second one is down. To find the net force, we need to add those vectors together. So there's this force of gravity between cow 1 and cow 2, plus this force of gravity between cow 2 and cow 3. My answer is then this net force here. So remember, we add vectors together tip to tail all the time. Now I know those values. So I want to find out what this is. So this is the net force. So if I think I can take either one, but I am going to use Pythagoras Theorem. Right? A squared plus B squared is equal to C squared. This is my longest side, so that will be my hypotenuse, the square root of A squared plus B squared. So my answer squared plus my answer squared, and then square root of that gives me 5.35 times 10 to the negative 7 newtons. That's the magnitude of the force. Probably want an angle as well. So tan of that angle is opposite over adjacent. You probably see right off the bat they're the same size, so it should be 45 degrees. So 3.78 times 10 to the negative 7 divided by 3.78, 10 to the negative 7. And then tan to the negative 1 of that is, sure enough, 45 degrees. So this is 45 degrees south of west. So we do need a direction as well. The big idea here, we need to add these vectors together tip to tail. I know in our forces and our kinematics is something we're still figuring out. And then we also need to remember these trig ratios. If I have these two sides, I can find the third using Pythagoras Theorem. And then I have my trig ratios of sine, which is opposite over hypotenuse, cosine, which is adjacent over hypotenuse, and then tangent, which is opposite over adjacent. So I also need those when dealing with two-dimensional. Kind of like in our force of gravity question early on, we're dealing with right triangles, and so we're dealing with Pythagoras Theorem and SOHCAHTOA when it comes to the analysis of that question. But most of the time, gravitational field. Now going a bit further, so we're looking at gravitational force. The next thing we're going to look at is gravitational fields. Gravitational fields explain gravity and how it acts over a distance. There's going to be a video posted this week that I suggest you watch if you are interested in learning more about gravity. But Newtonian gravity is incomplete. Einstein came along and he realized that there was a problem, and that problem actually came from looking at Mercury and seeing how Mercury orbits the sun. Newtonian physicists, they predicted that there had to be another planet there, and they called it Vulcan. Einstein looked at that and he did the math, and he actually expressed gravity as a space-time field, or a mass that will actually warp this field of space-time, kind of like you see here. You put something with mass in that field of space-time and it curves, and so that curve is what we experience as a force. Newtonian physics expresses it as a field, and field theory works. Like it explains things on the small scale, and the math works good when we're on the surface of the Earth and looking at things like that. And we use this idea in Physics 30 when we look at electromagnetism. But on the larger scale, it is the warping and bending of space-time that's actually a strength. So when we look at field theory, there's two formulas we need. So G is the gravitational field strength, and this is a vector at any point in time. If we look around this planet, okay, depending where we are, we'll experience a different force of gravity, and that should make sense, because if we're farther away, we're going to have less force. If we're closer, that force will be greater. We can see that by how close those lines are together. But a field kind of gives a value at a point in space at what's going to happen to an object. Now, we've already been looking at calculating gravitational field strength when we've looked at Newton's second law. Fg is equal to mg. The gravitational field strength is that 9.81. And we can calculate it if we have the force acting on something in that field and the mass of that object. That's one way to calculate gravitational field strength. Now, this depends on having information about the thing in that field. Another way to calculate gravitational field strength is taking a part of our Fg equals m1, m2 over r squared. It's kind of where both of these together come in. That's the blue part, Newton's universal law of gravitation. But we rearrange it, and another way to calculate G is big G times the mass of the thing causing the field divided by the distance from its center squared. Now this one requires us to know the mass of the object causing the field and how far away we are from it. So we could find that 9.81 by knowing the mass of the Earth and how far we are from the center of the Earth, just as easy as if we take our force and divide by our mass, we get that 9.81 as well. So those are two ways. One using the mass of the thing in the field, the other using the mass of the thing causing the field. Shows the strength, kind of what's going to happen at each point in space. It assigns a value. And we have two equations for gravitational field strength. The force on the object divided by the mass of the object in the field, or big G times the mass of the thing causing the field divided by the distance from its center squared. So let's determine the gravitational field strength at a point 25 meters away from a 50 kilogram mass as shown in this diagram. So if you think about at point P, it should be towards this mass. That should be the direction of the gravitational field strength. We know the mass of the object, so we know that one, and we know how far away we are from it. And it shows in the diagram that it is from its center. So the gravitational field strength is big G times my 50 kilograms divided by 25 meters squared. And remember that it's squared. So 6.67 times 10 to the negative 11 times 50 divided by 25 squared gives me 5.34 times 10 to the negative 12. If we want a direction, it's to the left, towards the center of that square. So we can get a direction because it is a vector, and we do need some units. So 1 unit is, if we think about G, 9.81 is meters per second squared. That's 1 unit that does work for gravitational field strength. Another unit is if we look at G. So G, big G is newtons times meters squared over kilograms squared. And then we're multiplying that by kilograms over meters squared. So we can get rid of that and that. Another unit is newtons per kilogram. And you might see that a lot talking about gravitational field strength. It's the amount of force per kilogram that gravitational field exists. So you can use the unit of meters per second squared, or you might see newtons per kilogram. Those are equivalent units. So one more question here. This now, maybe pause the video and try it. This is using the idea of both gravitational field strength and two-dimensional physics. This is the green sphere is going to exhibit a gravitational field strength at point P in this direction. And then we have the yellow sphere down here, which will exhibit a gravitational field strength in this direction. Now, I think the yellow one will be less because it seems to be further away. And it should be if we think about right triangles. But let's calculate each of them separately. So the green one is big G m over r squared. I need to use units of meters. So that's 6.67 times 10 to the negative 11 times the mass, which is 50, divided by 5 times 10 to the negative 2, because it's in units of centimeters. I want it in meters, and that's squared. So this is 1.33 times 10 to the negative 6 newtons per kilogram. And if I think about this one, I need to know r. So that's the longest side. C squared is equal to a squared plus b squared. So C, so I have 5 centimeters squared plus 5 centimeters squared. And square root that. So my r here is going to be this longest side will be 7.07 centimeters. So when I calculate G again, it's big G m over r squared. G 6.67 times 10 to the negative 11 times my mass of 50 divided by 7.07 times 10 to the negative 2. I want it in units of meters squared. And I get 6.67 times 10 to the negative 7 newtons per kilogram. And that should make sense. This should be less than the one above. because it's further away. Now the answer then, so we have this vector. We have our yellow sphere in that direction. So we need to take that vector and we need to add it to the green one, tip to tail, and we get our answer where that gravitational field strength will actually be the net gravitational field strength. So this again, 6.67 times 10 to the negative 7. This is 1.33 times 10 to the negative 6. Now you'll notice when you look at that triangle, so when we look at that triangle, that is not a right triangle. So we're not able to analyze it as a right triangle, but what we can do is we can split it up into components, or what we can do is we can use cosine law in order to analyze it. Cosine law is c squared equals a squared plus b squared minus 2ab cos of c. This is in your it's in your data booklet. Yeah, it's in your data booklet. It's a formula, so you don't have to memorize it. But we do need to label it correctly. So this is, if this is C, so if this side is C, then this is angle C. This is angle A, or angle A. This is side A. This is angle B. This is side B. Because sine law, you could also use sine law to analyze these. But if I want to find, we'll just find the magnitude. We want to find C squared is equal to A squared plus B squared minus 2AB. And then we need this angle, this cos C. So we do need to work that out. So we can kind of do some triangle stuff and see. So I know that this 5 and 5 on this diagram, I know that this is 90 degrees with the horizontal one. I know that this angle is 45, which means this is 45, which means this is 45. So this whole angle, angle C, is 45 plus 50. No, 45 plus 90, sorry. 45 plus 90 is cos of 135 degrees. So C squared is A squared, 1.33 times 10 to the negative 6 squared, plus B squared, 6.67 times 10 to the negative 7 squared, minus, and I'll do brackets, 2 times 6.67 times 10 to the negative 7 times 1.33 times 10 to the negative 6 times cos of 135. And then my square root that to get C. And I get a magnitude of 1.86 times 10 to the negative 6 newtons per kilogram. This is probably as hard as it gets. Now I use cosine law here. You could also use components. So you could split this gravitational field strength into this component and that component, add these ones together, and then find both the components for this larger right triangle. But cosine and sine law are a thing that work as well for these types of calculations. The big idea is when we find gravitational field strength or force of gravity in 2 dimensions, we need to be adding vectors tip to tail. This is as